Hi guys, it's Hamish back with another video, and today we're going to be talking about the Simpson's rule. Now, there are two very common ways of approaching the formula for the Simpson's rule. I'm going to have a quick look at both today and sort of explain why they're the same and go over some quick tips for always making sure you don't make a mistake when you're applying it. Okay, so the formula, as you will see it on the formula sheet for one application of the Simpson's rule, is as follows. The area under a curve approximated by a parabola is given by b minus a on 6 times fa plus 4, fa plus b on 2 plus fb. A lot of complicated jargon, but what it actually means is you take the value furthest left of the subinterval. This is two subintervals, so the whole interval. You take the value furthest to the left, you multiply that by 1. You take the average, so the midpoint across the whole interval, find the y value there, multiply that by 4, and then you find the y value at the right end of the interval and multiply that by 1. Add them all up, multiply it by the entire x distance of the interval divided by 6. And so when we're applying this formula more than once, so for example in two applications, we need to do it from A to B and then from B to C. And so when you add those together, you find that you get this big formula down here, and that the multipliers end up going 1, 4 times, 2 times, 4 times, and 1 times. And the reason for this is because we're taking two intervals, we do it from A to B and then from B to C. So what ends up happening is we add the y value at B twice. And so if this is a little confusing, don't worry. When we get into the example, it'll make a lot of sense. But the important thing is to remember this formula coming up. Basically, no matter how many applications you do, you're going to get this pattern of coefficients for the y values, this pattern of multipliers, if you will, where it's going to go 1, 4, 2, 4, etc., and then end with a 1. And in general, for n function values, this is the formula here. Now, something you might have noticed here is I've used this delta x on 3 out the front. But you might be thinking, oh, usually it's divided by 6, what's going on? So the reason for this is delta x, or as some people see it as h on 3, delta x or h here is the length of a subinterval, right? So that's the distance from, if we go back to the top, from A here to the midpoint between A and B, okay? As opposed to the distance from A all the way to B. So if we look at, that's h, and because it's the midpoint, this distance is the same, so that would also be h. So b minus a on 6, right? That's actually going to be equal to 2h on 6, which is h on 3. So essentially, if you use the length of each subinterval divided by 3, that gives you the exact same thing as if you were going to do two subintervals all divided by 6. So this is the version I use. It's up to you if you want to use the one from the formula sheet. If you understand which one you're using, you're not going to get it wrong either way. But most important is to remember these 4 things down here at the bottom. And these are that for the multipliers inside the brackets of the y values, the function values, the first and last will always be times 1. The second and the second last will be times 4 in every case. So if you've got one application, the second and the second last are the same. They're both times, they're the same value, so it's times 4. 5 function values, it goes 1, 4, 2, 4, 1. And with 7, it goes 1, 4, 2, 4, 2, 4, 1. So basically, the second and second last will always be times 4. And everything in the middle will alternate between 4 and 2. And then the last thing is that this is just a little thing a student told me. The Simpsons have 3 children, so you divide the subinterval length out the front here by 3. And that's how you get your h on 3. So enough of that, let's get straight into an example. Okay, so getting straight into our first example, use the Simpson's rule with 5 function values to approximate the area of the land. In this example, we don't actually have to calculate the function values, because if you imagine that this were a function on the Cartesian plane, then these distances here would be the y values as we move along the x-axis. So what it's going to end up being is the area is going to be approximately 150 on 3. It's the length of each subinterval, times 700 plus 4 times 1200 plus 2 times 1500 plus 4 times 1200 plus 700, and that's going to end up being 700,000 meters squared. And that's the first example done. Straight into the second example. This one is a bit more difficult because we need to create a table of values to find out our function values. So what we do is area between the curve lines x equals 0 and x equals 4. So what this actually looks like is it's going to be some curve going on like this. It's minus 1. And we're going to start at 0. X equals 4 is here. I want to approximate this area here. And so in order to do that, what we're going to do is we're going to use the function values 0 and 4, and the midpoint between them, which is 2. And so 1 on 0 plus 1 squared is 1. 1 on 2 plus 1, so 2 plus 1 is 3, so 1 on 3 squared is 1 on 9. And 1 on 4 plus 1 is 5 squared is 1 on 25. That's simple. So the area under the curve will be approximately the length of the summed interval, which in this case is 2 on 3 times 1 times 1 plus 4 times 1 on 9 plus 1 on 25, which gives us 668 on 675. Alright, I hope you found this video helpful, and most important is to remember those 4 tips, that the first and last multipliers are 1, second and second last are 4, everything else alternates between 4 and 2, and to remember to divide the subinterval length by 3. Okay, thanks for watching.